between the sender and the receiver chip to prevent the power being sent to an incompatible device. Then power is sent over all 4 wire pairs. So much like power over Ethernet, there are 2 categories. There's a powered device, which consumes power, and then power sourcing equipment, which is what sends power. So the key difference between HDBaseT and HDMI with TMDS is that whereas HDMI and TMDS is sending sending the data as a raw stream of bits, HDBaseT is packaged up into discrete packets. Instead of having dedicated wire pairs, we have dedicated packet types. So we've got our video packets, our RS-232 packets, IR, AV control, Ethernet, audio, and then other types of control as well. So it's not dedicated wire pairs, it's dedicated packet types. So any type of packet can be sent down any type of wire pair. If we look at the structure of the packet, it's divided into 3 parts. The header, which tells us what type of packet it is. The payload, where the actual data we want to transmit is stored, and then the CRC for deciding whether or not the packet is sent correctly and whether there's a transmission error. If you're familiar with Ethernet, you might see a similarity, but the key difference is there's no address in the packet. So that's one of the core differences between HDBaseT and Ethernet. So HDBaseT is only point-to-point, but by taking out the address, they could increase the overall bandwidth and payload size. So as I mentioned earlier, there's aspects of cadex cables that mean they aren't particularly suitable for sending the raw HDMI signal. They're much thinner, so they're more vulnerable to attenuation. And as I mentioned in an earlier session, attenuation increases at the higher data rates and frequencies. So it increases exponentially, and HDMI is using much higher frequencies than what cadex cables were designed for. Typical signal paths for cadex cables include patch panels, which aren't a problem for Ethernet, but they can cause reflection and add noise, which is a big problem for HDMI. And the different twist ratios for the different wire pairs, as I mentioned earlier, it's great for Ethernet, but not good for HDMI. So with that in mind, HDBaseT is based on the 10 gigabit Ethernet standard, and there are a few reasons why it's a good technology to use. So Ethernet has been around for over 40 years. It's been constantly improved and is still very widely used. There's clearly doing something right, and there's a lot of resources poured into making sure it keeps improving. Ethernet has a standard 100-meter transmission distance. You can basically do double what you can do with a very thick and chunky HDMI cable through a nice thin cable that you can terminate yourself. Transmitting high-speed digital data over long copper wires presents many technical challenges, and Ethernet has solutions for lots of them built into the standard. And yeah, as I mentioned earlier, the key difference between HDBaseT and Ethernet is that it's point-to-point. In a normal Ethernet packet, there is room for an IP address. In HDBaseT, we don't have that. So by using the 10 gigabit Ethernet standard, HDBaseT gets some nice features. We have error rate measurements thanks to the CRC check that comes with the packet-based architecture. We have reflection compensation, as the Ethernet standard is defined around using patch panels, and so it has an integrated solution for this. The different twist ratios in the Cat-X cable are no longer a problem. Attenuation can be compensated for, as there is an inbuilt monitoring of cable length and data rate. Different pulse amplitude modulation is used. We will cover this, but it basically means that we can send higher data rates through the cable without increasing the frequency. And by leaving out the addressing information, as I mentioned, we actually have more room in our packets for data, and our packets are simpler and faster to read and process. So what happens when we connect up HDBaseT devices? Well, instead of the basic handshake, we have what's called the startup period, where it actually configures itself for the optimal settings for that system. First, everything is silent and there's no connection detected. When a connection is detected, a training pattern is sent. This is a predefined pattern of information that is used to test the conditions of the transmission. It is used to adjust the different settings until the best possible mode has been selected for this transmission link. And once this process is completed, it starts the normal operation and sends data. So this this training pattern and this training part is it's very key for HDBaseT, and we'll see it's also something that happens in DisplayPort. And there's several things happening during this time. So one of the things is that it sets up the EQ level. So the training pattern is predefined, and so what is received can be compared to the known original transmission, and so the EQ can be adjusted until it gets as close as possible to the original pattern. Likewise, you can use edge finding to lock onto the symbols and the borders to eliminate any skew. So by doing this, it can do this on each individual wire pair, so the different twist ratios are no longer an issue because of this. So already we've compensated for some of the most difficult challenges that we had before HDBaseT. Okay, so let's talk about pulse amplitude modulation, or PAM. So as we saw in the earlier session with TMDS, we were using 2 voltage levels to represent binary ones and zeros. So we had a certain voltage level for a high voltage and another voltage level for a low voltage. With PAM, what we end up doing is using more than 2 voltage levels. There are different versions of PAM that correspond to the different number of voltage levels being used. So for example, PAM2 is what we've already talked about, where we've got 2 voltage levels and a high and a low. Each voltage level represents either a 1 or a 0. However, if we want to send data faster in a PAM2 configuration, then what we have to do is increase the clock speed. And if you imagine, you know, if we look at the end of this bit sequence, we've got a lot of transitions. If we increase the clock speed, then the time allowed for the signal to swing between the high voltage and the low voltage gets smaller and smaller and smaller. And if you to compensate for that, the swing has to get faster and faster and faster, and that's where you start to come up against issues that increase exponentially. So the sort of to increase the speed by double, let's say, it's going to take 4 times as much energy and generate much more noise. So the power increase for this and the EMI generated increase exponentially. But if we take a look at PAM4, here we've now got 4 different voltage levels, and each voltage level represents a 2-bit value. So by increasing the number of voltage levels, each one represents more information. So effectively, with the same clock speed, we're sending more information. We don't need to swing quite as fast between these different voltage levels because each one itself is actually representing more information. Likewise, with PAM8, we've got voltage levels representing 3 bits, and then with PAM16, they are representing 4 bits. So clearly, using higher PAM modulations has the advantage of being able to send more data per clock signal or clock cycle. But there is, as with many things, a trade-off. So the downside is if we take a look at the distance between these two voltage levels on PAM4,